Hello, class. Okay, so we finished one-dimensional kinematics, and now we're going to move into two-dimensional kinematics. And we have to define something called vectors before we can really get into this. So, again, this is in chapter 1 in the book, so I just moved it a little bit because we're about to use it now for what we do next. So, what a vector is, or let's just go back in one-dimensional kinematics. We talk about things like position, velocity, and acceleration. And we can, we need a coordinate system in mind in order to do that. If you're going to assign a number to like where an object is, well, it has to be like relative to what? I just say, where's an object? Well, it's 3 meters. Well, 3 meters away from what? So anyways, we need a coordinate system in mind. But now, say we have something that moves along a curve, really. Because, like if we have an object, say it moves from here to here in a straight line, that's still one-dimensional motion. We can just call that our x direction. We can put our, axes however we want. But if we have an object that does, say, something like this. Let's say it moves from A to B along this curved path. This is no longer a one-dimensional motion because it's moving on a curved path. So in order to describe motion like this, we're going to have an xy coordinate system. So now we can talk about 2 dimensions. And just to give you an example of how we're going to do this, key topic here is vectors. I'm actually going to erase this arrow. Let's say you start at point A and end at point B. Now remember in the one-dimensional case, we define displacement. Like say x equals 0, and we have an origin here, and let's say we start at A and end up at point B. And again, maybe the object started here and it did this. It went, way past B and then came, ended up at point B. We said the displacement is just the difference between these 2 points. It has nothing to do with, the actual path taken. It only depends on the 2 endpoints of the motion. And we can do the same thing for displacement here, where we just draw a line connecting these 2 points. And we give it an arrow to indicate that we are going from A to B. So this is a displacement vector. Let's call that vector A. Now when we write vectors, there's a couple ways you can do it. Sometimes what the textbook will do is use bold to indicate that we're dealing with a vector. Very hard to do that when you're writing though. So our notation is for a vector is we just put an arrow above it. Okay. And so we can represent this displacement with an object called a vector. But you can think of it as a directed line segment. So it has a direction as well as a length. And turns out that probably about half of the things that we deal with in this class are vectors. So if you go back to what we've done so far, we've talked about position, displacement, acceleration. You can say time because all these are functions of time. And so far, these 3, I forgot velocity somehow. And then I'll put time here. So out of these things, these are all vectors. And time is something called a scalar. So pretty much everything we do here it's either going to be a vector or a scalar. Now there are other things in physics that aren't really either of these. There's things called tensors that are more complicated than vectors, but we're not going to do that, so we don't have to worry about it. So basically everything we do is a vector or a scalar, and yeah, so far most of the things we've been talking about are vectors. But we've only been dealing with one dimension, so it's very easy to deal with vectors in one dimension. The key thing about a vector is it has a direction. And yeah, it has a magnitude and a direction, where time is more just a magnitude. You know, how long was something? It was 5 minutes long. You don't ask like what direction that was. Yeah, like displacement. That would be, you know, to say I traveled 3 kilometers, well, it doesn't tell the whole story. You could be going in different directions. So to really describe that motion, you need to know what direction and also how far you moved. And I think, just basically think everything that has a magnitude and a direction is a vector, and everything else is a scalar. And actually that is not true. There's more to a vector than just being a magnitude and a direction. We'll actually see an example of that, where something has a magnitude and a direction, but it's not a vector, but we'll talk about that when we need to. There's a little more to vectors than just having a magnitude and a direction. Let me just give you an example of that. Let's keep our XY coordinate system here. Let's say that we start at point A, and then we move to point B. So we can represent that as a vector. And then let's say from point B, we move to point C, which we can represent as another vector. So we have A, B. We can describe this vector as AB, like it's one single thing. We're sort of describing it this way. So that goes from point A to point B, and we have vector BC. And the net displacement, we can call AC, because it goes from point A to point C. And we can write an equation here, like AC equals AB plus BC. So like you have the same result. If you start at point A and you go to point B, and then from B to C, you know, the net displacement is the same as just starting from point A and ending at point C. So anyways, to get back to the point, what if we have AB plus BC is equal to AC? Another property of vectors, though, is we can reverse this order. So when we're going to define vector addition later. And like right now we added these two vectors. We take vector AB and then we add vector BC. However, we could have done it the other way around. We could add vector BC and then add AB, and we'd get the exact same result. So that's another essential property of vectors. And later on, we're going to talk about something that does have a magnitude and a direction, but it doesn't obey this rule, that you can reverse the order. So, yeah, just think vectors have a magnitude and a direction, but not everything that has a magnitude and direction is a vector. Okay, so what I want to do is I want to give a kind of, maybe I should have left that picture there, but I want to give a formal definition for, there's two things we need to know, two like mathematical operations we need to know about vectors. And that's addition and something we call scalar multiplication. And so I'm going to define those. But before we do that, we have to review a little bit something about basic triangles. So we're going to start with a simple right triangle. So say this is a right triangle, that would be our right angle. And across from the right angle is the hypotenuse. And I'm going to call that R for reasons that might be clear later. I And we'll call this x and y. And we'll say this angle is theta. Okay, now we're going to find three functions, which are called sine, cosine, and tangent. So sine of theta is y over r. I'm just going to write them down first. Cosine of theta is x over r. And tangent of theta is y over x. So first, let's just look at the triangle. It has a right angle, and so we know the opposite the right angle is going to be the hypotenuse. And if we have this angle, we can define the other two sides, like this side here is connected to the angle. So we call this the adjacent side. The longest one is the hypotenuse. And the one opposite the angle is called opposite. So, say sine of theta is opposite over hypotenuse, or y over r. Cosine of theta is adjacent over hypotenuse. That's x over r. And tangent of theta is y over x. And so this is probably how you learned about these functions. There's actually a better way to define them, though, because there's a bit of a problem. Like, we want theta to be anything. So if we have theta, like, say, 20 degrees or something, we can draw this triangle. But what if theta is more than 90 degrees? So like here, we typically draw the triangle like this. But what if theta is more than 90 degrees? Yeah, we don't really have normally if we were to, let's say this is a 120 degree angle. I mean, if we want to just draw a triangle, it would be like this. We no longer have a right triangle. So what we could do is draw a triangle, just like add a side over here, and this would be a right triangle. But there's a better way to approach this. I guess another problem with defining functions like this, or in terms of triangles, is what if theta is 90 degrees? We don't have a triangle anymore. It just becomes a vertical line. If you picture this angle increasing, this one keeps moving over and growing, and when you reach 90 degrees, we'll just have a vertical line. So how can we even deal with, we don't have a triangle anymore. So we kind of need a better way to define these functions. So I'm actually going to erase this. Okay. And I'm going to draw something else called the unit circle. And if you were wondering before when I drew that triangle, why am I calling things x, y, and r? Well, hopefully that'll be clear in a moment. So here we have a unit circle. Now, unit in math just means like 1. So this is a circle with a radius of 1. Now, in general, though, you could give it a radius of r, but let's just say it is a radius of 1. And so if we look at this point on the unit circle, that makes an angle theta with respect to the x-axis. The coordinates of that point, is coordinates xy. But what we can do is we can drop a vertical line here. And now we have a right triangle, where this side is x and this side is y. So remember, based on this right triangle, like sine of theta is y over r. But if it's a unit circle, r is 1. So sine of theta is just y, and cosine of theta is just x. So the coordinates of this point are cosine theta and sine of theta. And again, this is for a unit circle. which means it has a radius of 1. If you want a different radius, you could just have r here, and the coordinates would be r cosine theta and r sine of theta. But why not just make it 1? Now, the advantage to the unit circle approach is, let's look at an angle like, say, 90 degrees. So 90 degrees would be right here. The x-coordinate is 0. So cosine of 90 degrees equals 0, and sine of 90 degrees would be 1. Like the coordinates of this point, the x-coordinate is 0, the y-coordinate is 1. And if you look at, say, 180 degrees, so yeah, this was 90 degrees. So at 180 degrees, the coordinates of this point are -1, 0. So cosine of 180 degrees is -1. Sine of 180 degrees is 0. And so, this works whatever your angle is. It works just fine with negative angles. So the convention in, just in math, you measure angles from the positive x-axis, and the convention is you always go counterclockwise. So like, remember the quadrants? Might look weird when you first see this, but there's 4 quadrants, and it looks like this, 1, 2, 3, 4. I remember the first time I saw that, I thought, why would they do it that way? That just looks strange. But, yeah, it's just, the way we measure angles, this makes sense. We start in quadrant 1, and then we go to quadrant 2, 3, and 4. And we can also handle angles greater than 360 degrees. There's a rule, like for any trig function, let's just say like sine of, say, 500 degrees. That's also equal to the sine of 500 minus 360 degrees, which would be sine of 140 degrees. So like you can subtract 360 degrees. If you just picture this angle of 500 degrees, you start here, you go around 360 degrees, you're back exactly where you started, and then you go an additional 140 degrees. And so you'd end up, these two angles are going to end up at the same point on the unit circle. And so these trig functions are cyclic. Every, tangent repeats itself after every 180 degrees, but sine and cosine repeat themselves after 360 degrees. Okay, so unit circle, very good way of looking at basic trig functions. All right, that kind of leaves an issue of how would you actually calculate that? Like, sine of 30 degrees, that's exactly equal to 0.5. That's one of those special angles. So like 30, 45, 60, any of these 0 or multiple of 90 degrees. Those have exact values, but what about like the sine of 12 degrees? Well, all you do is go to your calculator. That's actually a big problem. How do you calculate the sine? Like, you ever think about that? Where do those numbers come from? You just plug them in your calculator, it gives you an answer. But what if we didn't have calculators? It's not something we're going to get into in this class. If you take Calc 2, you'll learn how to do that. So, yeah. Okay, so little basics about triangles and the unit circle. There's one more thing. I'm going to draw this. I'll just erase the unit circle. Let's look at this triangle again. We have a right triangle with sides x, y, and r, and a very important relation between them. We have x squared plus y squared equals r squared. That is the famous Pythagoras Theorem that goes back thousands of years. I think in Egypt or Babylon or something, they actually found this on a tablet, like chiseled into a stone tablet. Not in an equation form, or in a graphical form, but Yeah, so very, very important equation. So again, x and y, these are the lengths of the smaller sides. R is the length of the hypotenuse. So that's the Pythagoras theorem. And there's something really nice. We can write this in another way, which turns out to be very useful. Let's divide both sides of the equation by r squared. Now again, we have a, you can break up in the numerator, you can write this as x squared over r squared plus y squared over r squared. It's two separate fractions. But x squared over r squared is just x over r in parentheses squared. And y over r, same thing here. And r squared over r squared is 1. And if you look at this, x over r is cosine of theta. Y over r is sine of theta. So we can write it this way as well. This is really just another way of writing the Pythagoras theorem. Sine squared theta plus cosine squared theta equals 1. It's called a Pythagorean identity. I guess it's a little different because it doesn't necessarily have to do with triangles. This would work for any angles. Even, not just like between 0 and 90 degrees. Okay. Now the reason that we needed to go through this background is because vectors have magnitudes and directions. And so let's say this is a vector r, which points in this direction. It's very important to be able to do something called breaking this vector into components. So if we just have this vector r in an xy coordinate system, what it means to break this vector into components is to complete this triangle where you go like a certain distance in the x direction and then a certain distance in the y direction. So if this is r, that's our vector r. Actually, I'm going to do it like this. Now, we say a vector has a magnitude and a direction. Just notation-wise, if we write it, one way of saying like the magnitude of a vector is to just write it without the arrow above it. So like vector r, we write like this. The magnitude of r is just r. We'll talk about other ways of writing magnitude, but for now we'll leave it at that. And if this vector r makes an angle theta with the x-axis, then we can say this side is r cosine theta, and this side is r sine theta. So our cosine is the one adjacent to the angle, and sine is opposite the angle. So that's one of the very important things that we need to learn how to do with vectors. It's called breaking it into components. And actually, components, there's different ways you can define vectors, but we're going to actually go with defining them in terms of their components. So I'm going to kind of define a vector. There's kind of two ways to approach vectors, algebraically and graphically, and they're, of course, connected to each other. But we're going to kind of, for the purpose of definitions, we're going to go with an algebraic approach. So we're going to find a vector, let's say a general vector, we'll call it A. Now vectors can actually have any number of dimensions. You can have a one-dimensional vector, which I guess we kind of covered that without calling them vectors. But remember, like displacement can have a direction, which we just indicate with a positive or negative sign. So in 2 dimensions, we can have a displacement vector where we need more than just a plus or minus sign. But you can also have a 3-dimensional vector. And vectors can represent so many things, they don't have to be things you can even visualize. So you could have a 12-dimensional vector if you want. But we're going to stick to 2-dimensional vectors. And so it's going to have 2 components. And there's different notation for this. I kind of like this notation, where we use these kind of carets to write the vector. Another common notation, though, would just be like parentheses. And again, either one is fine. The problem is this can sometimes be mistaken for just like coordinate points. So like if you have an xy plane, like say you have a point, say 1, 3, you would write it like that, where a vector is a line segment, not a point, which is why I decided to go with this notation. But again, it doesn't really matter which notation you prefer. Different ways of saying the same thing. So it's not a big deal, but yeah, so we're going to find a vector in terms of components. But again, vectors have directions, and so we always want this graphical approach to it as well. So I want to kind of do them both at the same time. So this will be like our formal definition of what a vector is. But let's look at an example. Let's say A is vector 2, 4. Now we can represent that graphically as a vector that goes, say, 2 units in the x direction and 4 units in the y direction. So that would be vector A. You go 2 in the x direction, 4 in the y direction. You can maybe see that this represents a lot of, this could represent a lot of things. It could represent a displacement that starts here and ends here, or maybe the velocity. Something is moving in that direction, or accelerating in that direction. Later we're going to talk about forces, which are vector, and forces have direction. You apply a force in a particular direction. So, yeah, we're going to go with this component form, though. But yeah, this is the x component of the vector. That's the y component. So you go 2 in the x, 4 in the y, and that gives the direction of the vector. Okay, now you can look at another vector, say 1, 2. Let's say B is a vector 1, 2. See, like B, these two vectors are going to point in the same direction, but they have different magnitudes. All right, so that's kind of how we define vectors. One more important thing. Let's stick with this example. Now, we usually have a coordinate system in mind, and we can draw this vector in a coordinate system where let's say we looked at the point 2, 4. So vector A would start at the origin and point at, then, it would terminate, say, at that point 2, 4. However, the vector exists independent of the coordinate system. So you could just as well, let's say we could start at this point here. If you go over 2 in the x and up 4 in the y, this vector is also A. These two vectors are exactly the same. So vectors actually can be used to represent things where, like, the location of the vector is very important. But vectors themselves don't have a location. These two vectors are exactly the same. So that's kind of an important point. They don't have an actual fixed location, but sometimes they're used to represent things that do. Okay, so this is how we define vectors, just a collection of points. And vectors have two properties that we need to know. Those are vector addition and I think I'm actually, well, yeah, I'll write it down. Let's say we have A plus B. We have two vectors, A plus B. Okay, now, okay, here's A. Let's write vector B. I say -1 and -2. So A and B. All right, now how would we define the addition of these two vectors? Now, the simplest vector to imagine is a displacement vector. So let's draw a coordinate system. You know what, I'm going to change this. I just realized those numbers I picked weren't good. Or, not great anyways. So, anyways, let's do that. So, let's start at the origin, and let's say vector 2, 4. You go over 2 and up 4. So that'll bring you to this point. This is vector A. Okay. Now, let's say at this point now you're here. What if we apply vector B as another displacement vector? So that means we go over 1, we go, negative. So that'd be to the left, and then we go down 3 because, up is our positive direction. So vector B, it would go over 1 and down 3. Eraser just fell apart. All right, so I think I want to change these numbers again. Just I should think about how this is going to look overall. Yeah, sorry about that. Let me just change these numbers because these two vectors are so close to being parallel. Might be hard to see. So maybe it'll be better to do this. Let's just change it just for, everything we said applies just like before, but I think the graph will be a little cleaner if we do it this way. So A is 4, 2. So this is vector A. Let's change this one as well. I just want to make a clear graph. So that's vector A. And then vector B goes from -1, and then it goes up 3. Yeah, this is a much clearer graph. So that's vector B. So again, vector A, doesn't matter where you start, but just for convenience, let's start at the origin. So we go over 4 and up 2. And then vector B, we go -1 in the x direction and up 3. Okay. Now, again, we're thinking displacement vectors here. So let's say you start here, and you go through the displacement A, and then you go through displacement B. Where are you going to end up? This would be A plus B. This vector that starts at the same place A started and ends where B ended up. Where you eventually ended up after going through these two displacements. So, we're using this to motivate our definition. Like we created vectors, which was a guy named Gibbs that invented vectors. And you're free to define things however you want. So, but again, you want to define things in a way that's going to turn out to be useful. And what is the net result? Like, where are we going to end up? If I drew this accurately, let's try and see. Okay, I didn't draw the best picture, but it looks like the coordinates of this point are 3, 5. Our final destination here is 3, 5. Again, maybe not the best picture, but you can see if you add these two vectors, we can represent the net displacement, the result of each of these, as starting at the origin and ending up at that point 3, 5, where if you add 4 and -1, you get 3, and 2 and 3 gives you 5. So again, vector addition is actually extremely simple. Just when you have these in component form like this. Yeah, I mean, it's about the simplest way you could add two things like this. Just add the x components to get the x component of, it's called the resultant vector. Like A plus B is the resultant vector. So it has two components. So to get the x component of the resultant, you add the x component of whatever vectors it's made up of. Same with the y direction. So let me write this. If you just look at the formula, it might look kind of complicated, but it's really not. So again, if you just want to add these vectors, 4 plus -1 is 3. 2 plus 3 is 5. very easy. Okay, now, so that's called vector addition. And again, now let's talk about graphically how you add vectors. There's actually two ways to do it, graphically. What we've drawn here is called the tip-to-tail method. So, we draw A, and then we draw the tail of vector B at the tip of vector A. And the resultant vector starts at the tail of A and ends at the tip of B. It's called tip-to-tail addition. There's another way to do it, though. And basically, remember I mentioned earlier a critical rule for vectors is like A plus B equals B plus A. So you could do it that way. Like you could start at the origin and you could take vector B, which points in this direction, and then vector A, which points in this direction, and you'll end up at the same place. And so we can also define a graphical way to add vectors called the Parallelogram Rule. And this is very useful if we're talking about something like forces. So let's say we have an object, and let's say this is just some object, and we apply two forces, F1 and F2. So again, it's really nothing different than the tip-to-tail method. You can just add these in the opposite direction. But you can see the resultant vector is just the diagonal of that parallelogram. So remember, we can move vectors around, but that doesn't change the direction. So like this is vector A, that's vector A as well. And so these two lines are parallel. And that's vector B, that's vector B. These two are parallel. So they form a parallelogram, and then you just draw the diagonal, and that's the resultant. And so if you have, like, say, two forces acting on an object, we want to draw them because the location where the force is applied can be important. So we might want to draw an accurate force diagram. And then what we can do to add these two vectors graphically is let's draw a line parallel to F1 that's passing through the tip of F2. And then we draw a line parallel to F2 passing through the tip of F1, and that forms a parallelogram. And the sum of these two forces would be that diagonal. So I call the resultant, I'll call it R for now, just R. So that's how we add, there's two ways, the tip-to-tail method where you do that. And again, tip-to-tail, think displacements. You do one thing first and then the other. So you go from here to here and then from here to here. So tip-to-tail method is a natural way to describe that. Again, if you apply two forces at the same place, you want to draw them at the same place. And so then you'd use the parallelogram method to find the resultant graphically. Okay, so that's one of our rules, and that is vector addition. There's another one called scalar multiplication. Scalar multiplication. Now, can give you an example of this, a relevant one because it's physics. This is one of the most famous equations, so there's a good chance you've heard of this before. But very important equation called Newton's second law. Force equals mass times acceleration. Now, we know force and acceleration are vectors. So we could write it this way. And if we have multiple forces, we'd have to add up all those forces. We call that the net force. So again, this is Newton's second law. And on the left side, we have like a sum of all the forces acting in an object. On the right side, we have the acceleration which is a vector. We're multiplying it by the mass, which is a scalar. So that's why it's called scalar multiplication. Now, you might be wondering, what about these two vectors, A and B? Can you multiply two vectors together? And the answer is yes. Are we going to do that? kind of and kind of not. This is one of those things I kind of wrestle with a little bit, and I've done it both ways, but basically I don't mention multiplication of vectors, even though we will be doing it relatively often. We're just not going to call it that. There's actually two ways you can multiply vectors. One is called scalar product, the other is a vector product, or a cross product, you might have heard. But we're not going to do that. So, but just to explain why this word scalar there. We're multiplying a scalar and a vector. And the rule for this is about as easy as anything could be. So let's say A is our vector, ax comma ay. Let's say we multiply it by c. Then we have, just write down the formula. So again, this is about the simplest rule that you could imagine. Like, say you have vector A is 2, 4. What is 2A? Well, I just multiply each of these components by 2. So 2A would be 4, 8. Again, very simple rule. And let's kind of look at how this would look graphically. If we have A is a vector that goes 2 in the x direction and 4 in the y direction. So that's vector A. Should make it a little steeper. Okay, now vector 2A, that's going to go, twice as far in the x and twice as far in the y direction. So vector 2A is going to point in the same direction, but it's going to be twice as long. So basically, if you multiply a vector by a scalar, you're not changing the direction, you're just changing the length. There is an exception to that, though. What if we look at minus A? So really, it's like minus 1 times A. So that would be minus 2, minus 4. And so you go 2 to the left and 4 down. So that would, minus A would look just like A, except it's rotated by 180 degrees. So if you look at like minus 2A, what you do is you take that vector A and you rotate it through 180 degrees, and then you double the length of the vector. Okay, so those are our two rules for addition and scalar multiplication. Okay, so talk about, leave that up. Okay. Now, one of the main things that we want to do is be able to add vectors. And, all right. So, one of the main things we want to do with vectors is be able to add them. And, let's stick with this. We've done well with this vector. A concrete example, say 2, 4. And I'm going to draw this here. So we go 2 in the x direction, 4 in the y direction. And again, the way we define vectors, this is component form. There's another way that we can describe vectors, and that is in polar form. So this is a vector in component form. Now, polar form is kind of a more natural way to describe a vector, because vectors have a magnitude and a direction, and that's what polar form is. You describe it in terms of its magnitude and direction. And so we need to be able to convert between the two. Let's see, we want to be able to go from component to polar and the other way around. So from component to polar, or polar to component. You got to be able to do both of those. So let's start out with something in component form, and we want to find the polar form, which means its magnitude and the direction. So what we can do, let's define this angle here as theta. So what we need, so there's our direction, theta. We have to be able to find numerically what theta is, but we also need to find the magnitude. And again, just by drawing this as a triangle, the magnitude is very easy to get, just using the Pythagoras Theorem. So here we'd have 2 squared, which is 4. 4 squared is 16. Add that up, you get 20, and take the square root. So to find the magnitude of this vector A, I'm going to use a different notation for magnitude. This is also used for magnitude, like absolute value signs around it. But what you do is you do ax squared, you square the components, add them up, and take the square root. So basically, Pythagoras Theorem. Now for the angle, let's just look at this triangle. I'm going to use tangent here and say tangent of theta is 4 over 2. Now you could use any of the trig functions. You could say sine of theta is 4 over the square root of 20, but I don't like doing that because that introduces an additional source of error, an additional chance to screw things up. Because like this vector, say you were given this vector, you know these numbers are good. And so, yeah, you can use those. But what if you screw up calculating the hypotenuse? If you use sine or cosine, then you'll get the wrong angle as well. So a little safer just to stick with tangent. So if we have tangent of theta is 4 over 2, how do we find theta? We take the inverse tangent. So in general, it'd be ay over ax. So if we have component form, we can convert to polar form where we have the magnitude and the direction. Unfortunately, it's not quite as easy as it looks. And the reason why is this inverse tangent, which is a bit of a problem. So I'm actually going to erase this. Let's look at inverse tangent. Yeah, let's look at this example. I'll keep this vector here. Yeah, I'd say we go over 2 and up 4. Okay, so there's our vector A. And if I tell you, tangent of theta is 4 over 2, or 2, if I tell you theta is equal to the inverse tangent of 2, do you know what theta is? And, well, you can pull out your calculator and take the inverse tangent. Let's do that. So inverse tangent of 2 says 63.4 degrees. Okay, so there's our angle. Now the problem is, and we already know the magnitude of this is the square root of 20. We can simplify that algebraically, but who cares? Okay, so here is the polar form of that vector. The problem is, are we sure that's the right angle? Now, ultimately, it comes down to theta is the inverse tangent of 2. It's not a question of did we make a mistake? Like, did we plug something in the calculator wrong? No, the question is, what if we have I'm going to define a different vector, b. where b would have components of -2 and -4. So if we use this, this formula I wrote down, remember we said theta would be the inverse tangent of, well, we said ay over ax, here would be by over bx. We'd have -4 over -2, which is the inverse tangent of 2, which is the exact same angle. And so if you just kind of blindly take the inverse tangent of these two vectors, which are obviously very different, you're going to get the same numerical answer. Now, why is that the case? And the reason why is because this tangent function, actually, let me be clear on this. Let's draw tangent graphically. Or you know what, I think you might be more familiar with the sine function. So let's draw the sine function. We'll graph it. So let's say theta and sine of theta. And, say 90 degrees, and then 270. Okay, so this is sine of theta. And if you look on your calculator, of course, you have an inverse sine function. So does this function have an inverse? And the answer is no, it does not. Now, why does your calculator say that it does? So we have to look at what a function is and what an inverse is. So let's start out with what is a function. Like, let's say f of x equals x squared. Is that a function? Yes, it is. And the kind of rule is, if I give you x, can you figure out what f of x is? And the answer is yeah, no problem. Like, take f of 3. That equals 9. You plug in 3 and you square it. Is there any question that the answer is 9? No, not at all. But what if I tell you that f of x is equal to 9? Do you know what x is? And the answer, not necessarily. Because it's also true that f of -3 is equal to 9. So if f of x is 9, that means x could be 3 or it could be -3. You don't know. And so, for a function, there has to be just one answer to it. You plug in x and you get y. So for an inverse function to exist, so there's a test graphically. Let's go back to sine now. So I'm sure you remember this, the vertical line test. Draw a vertical line if you cross the function at only one point. Then it's a function, but that only works if you can do that for any, any vertical line that you draw. So just to be clear, if you have something like this is not a function. You can draw a vertical line that's going to cross at one point here, but if you draw a vertical line there, it's going to cross at 3 points, and so this is not a function. So again, in order to be a function, every vertical line has to cross the function at exactly 1 point. That's why if we plug in 3, we get 9. There's no question about that. But now, in order to have an inverse, we want to be able to go the other way. Like here we had, in this example, tangent of theta equals 2. What is theta? So we want to be able to go the other direction without any ambiguity. And so in order to have an inverse, a function has to pass the horizontal line test. So if you draw a horizontal line, you only cross the function at 1 point. Here, that's clearly not the case. So like here, if I say sine of, let's say this value is y equals 0.6. So again, let's say that sine of theta equals 0.6. Do we know what theta is? No. It could be this value, whatever this x-coordinate is. It could be that value, or this one, or this one. There's actually an infinite number of solutions to this equation. And so basically what that means is that the sine function, just like cosine or tangent, none of the trig functions actually have inverses. I'm going to redraw the sine function again. I'll try to just retrace. Okay, so here's our sine function, and this fails the horizontal line test very badly. So what we do, in order to define, we need an inverse trig function. We need to be able to solve equations like this. So what we do is if we restrict the domain, like for a sine function, if we stick between these two values, here, minus 90 degrees and 90 degrees, just from here to here. So actually, let me erase, or here, let's kind of make this a dotted line for the rest of it. So yeah, we kind of just cut off everything else. And so this function only exists between minus 90 and 90 degrees. Then this function is has an inverse. That's called the one-to-one function. For every x, there's only one y, and vice versa. So we're good here. We can define an inverse just for this part of it. And the consequence of that is if you take an inverse sine, we're looking at from minus 90 to 90 degrees, we're getting quadrants 1 and quadrants 4. So whatever you plug in, like, if you plug in a positive value, like sine, inverse sine of, sorry, that's plus 90. Like say inverse sine of 50 degrees. Let's just do that. Oh wait, sorry. That made no sense. But I mean, like say we plug a positive y value. So inverse sine of say 0.5. That'll give us 30 degrees. So 0.5, that's 30 degrees. Now if I take the inverse sine of a negative number, then we're going to get a negative angle. So it'd be in quadrant 4. So it's a minus 0.3. Yeah, we get minus 17 degrees. And so if you want, again, if you have an equation like, say, sine of theta equals 0.5, for example, again, you can, remember the peak here is at 1. Remember from the unit circle, like sine of 90 degrees is 1. You're never going to get higher than that. So 0.5 would be like this line here. Again, there are an infinite number of solutions. You just have to know which one it's going to tell you. It's going to tell you the one in quadrant 1 for the sine function. And you can use that to find all the other solutions. But we're not going to bother with that. This is more just when you are dealing with inverse functions in general, you want to be very careful. If you're dealing with the inverse of a trig function, you definitely want to be careful because none of the trig functions even have inverses unless you restrict your domain. And there can be real problems where if you just plug it into a formula and you can get the, you'll get the angle, a different angle than the one you're looking for. So the solution is to just be careful and always draw pictures. Like if you go back to that example, B is -2 minus 4. I think the angle was, here, let's do inverse tangent of 2. If, 63.4 degrees, again, you go from the x-axis, go 63 degrees. Well, clearly this vector is pointing in the wrong direction. So you know you've made a mistake there. So, and again, it's the actual vector is just 180 degrees. It's just pointing in the opposite direction. So again, just always draw a figure to go along with anytime you're dealing with vectors and finding angles. It's a very good idea not to just rely on the equations, but always draw a picture and have an image of what it should look like as well. Okay, so that was the hard one. Going from component form to polar form. Going the other way around, that one's actually kind of easy because you don't have this ambiguity before. Like if you have a vector in polar form, you know what the angle is. That's where the confusion can come from. Just the definition of that angle. So if you have a vector, if you're given the polar form, and this is how it's typically written, like the standard form. Say vector A equals 9 at 120 degrees. So you just write x and there's the angle. And if you write it like this, it's implied that this is the standard way of measuring angles. So like here's xy. So again, you'd start at the x-axis and rotate 120 degrees. So that would be vector A. And you have this vector has a length of 9. Now there's two ways you can do this. One is kind of a standard way. You can say AX is equal to A cosine theta, and AY is equal to A sine theta. And that always works. If your angle is given in the standard form, like you start from the x-axis and go counterclockwise, then this method always works. Another way you can do it, though, is kind of a geometric approach. Like, say this is 120 degrees. That makes this angle 60 degrees. Because, you have to add up to 180, going from the positive to the negative x-axis. And so now we have this triangle with a hypotenuse of 9 and a 60-degree angle here. So we could say that this is 9 times cosine 60. And this side here is 9 sine 60 degrees. But there's one more thing we need to do. Put a minus sign in front. So let me actually do this. I'm going to take 9 times cosine of 120 degrees. Minus 4.5. So, nice number. Can remember that. Okay, so minus 4.5. So it gives you the minus sign. If we do it this way, cosine of 60 is positive. Cosine of 60 is 0.5. If you multiply 9, you get 4.5. So you have to put that minus sign in yourself. But again, it's kind of obvious if you start at the origin to get to where this vector is pointing, you have to go in the negative x and positive y. So if you want to do it this way graphically and kind of make a right triangle out of it, then you're dealing with an angle between 0 and 90. So it's always going to give you positive numbers. But if you have the picture, you can easily tell what each component is going to be. Is it going to be positive or negative? Okay. Now, so yeah, this going back and forth between component form and polar form, extremely important. And the reason is that vectors naturally come in polar form. It's like, say you exert a force, it points in a certain direction. And, so it's like a certain amount of force pointing in a certain direction. Or displacement, that direction, go 10 miles in that direction. So this component form is more of a mathematical thing. It doesn't exist naturally, but component form is so much easier to work with than polar form. Now there are ways of adding vectors in polar forms. Polar form, that's one of the main things we want to talk about is adding vectors. And you can add vectors in polar form using things like the law of sines and the law of cosines. It's probably never worth the trouble doing that. So if we want to add two vectors, let's say we're given two vectors in polar form. Let's say A is 3 at 12 degrees, and vector B is 5 at 42 degrees. So graphically, you've got vector A and vector B might look something like this. You want to add them up. Forget about trying to do it graphically using the law of sines and law of cosines. The process is break A and B into components. And once you're in component form, you can see adding them up is going to be the easiest thing in the world. You can often collect it as a graph, like say vector A, B, and A plus B. And then you have an X and a Y component for each. Why don't we actually do this one? So this is 3 at 12 degrees, so the X component would be 3 times cosine 12. Which is around 2.93. And the Y component is 3 sine 12, which is 0.62. Now vector B, that's 5 times, the X component we multiply by cosine, that's 3.72. And then for the Y component we use sine, 3.35. So again, break vectors into components, and now if we want to add A and B, we just add the components. So very, very easy to do. And now we have A plus B. However, it's in component form, and maybe we want the answer in polar form as well. So like here, then you add, and then maybe you want to convert back to polar. Maybe you want to just leave it in component form, depends on what you're actually doing. But again, now we can find the magnitude of this vector using the Pythagoras Theorem. We square this number, square that number, add them up and take the square root. And for the, let's do that. Let's see. The magnitude of A plus B. So 6.65 squared plus 3.97 squared. Now I'm trusting the calculator to square first before adding them because that's what it should do. What I'm getting is 59.98, let's just say 60, and then the square root of 60, that'd be 7.75. And again, that seems, pretty reasonable. And now for the angle. Now again, we're going to be in quadrant 1, so there's definitely not going to be an issue taking the inverse tangent here. So I'm just going to do it without drawing a picture, even though I said not to do that. But we do kind of have a picture. We're going in that direction. Remember Parallelogram Rule? A plus B is going to look something like this. So we're in quadrant 1. So we will definitely not run into any problems here. So I'm just going to take the inverse tangent of 3.97 over 6.65. That's 31 degrees, roughly. So, we added these two vectors now. So we did this in this kind of roundabout way, where first we convert each of these vectors into component form, and then we add them, which is completely trivial, and then convert back to polar form, which isn't that hard either. And yeah, much easier than trying to do this geometry stuff with law of sines and law of cosines and all that. Okay, so we've got one more thing to talk about, and that is we're going to do at least one example of a three-dimensional vector. Oh, actually, sorry, we have two things to talk about. I forgot one thing I just realized. But I'm going to make up a vector. Let's say A is 3, 5. Okay. Now there's another way we can write this, which is actually a very nice way of doing it. But first, I'm going to use our rules for addition and scalar multiplication. We can write this vector as 3, 0 plus 0, 5. So again, just 3 plus 0 is 3, 0 plus 5 is 5. And then using scalar multiplication, we can write it like this. If you just kind of go from this, it's kind of easier to see it backwards. If you multiply 3 times this vector, you get 3, 0. If you multiply this, you get 0, 5. And so what we do, if we look at this vector, this is a vector that has a length of 1, and it points in the x direction. And so this is what, these are both examples of what we call unit vectors. Unit means 1. Both of these vectors have a magnitude of 1. This one points in the x direction, and this one points in the y direction. And so we give them names, and there's different names depending on which book you use. I like just calling it like x, defining these vectors, these unit vectors. Now normally we put an arrow over a vector. However, if it's a unit vector, we put this called like x hat, just to signify it's a unit vector. So this points in the x direction has a magnitude of 1. Y hat would be, point in the y direction and have a magnitude of 1. And so you could write this vector A in this form, 3x hat plus 5y hat. So it's just a different way of writing this. So it basically means 3 in the x direction, 5 in the y direction. It's a very common type of notation and pretty useful. Oh, yeah, the other notation though, a lot of books, instead of calling it x and y, they'll call it I and j. So just a preference, whichever way you like it. I like x and y, it just tells you that's the direction. Okay, so and again, one reason we're talking about this, although it's not maybe necessary, but this is usually how you'll see vectors written. And yeah, like after the exams, I'm going to post the solution to the exams on Canvas, and I often write it in this way. So just so you know what this means. Okay, I know this is kind of dragging on, long topic. We have one more topic to consider, and that is a three-dimensional vector. We'll look at it in terms of an actual concrete problem. This works a lot better in an actual classroom, I think, but because we can use our room as an example. So picture whatever room you're in. Hopefully it's rectangular, in a circular room or something. But let's look at this point A. Let's say that is one of the corners of the room along the floor. And let's say point B is the opposite corner, but on the ceiling. And the dimensions of the room, let's call those X, Y, and Z. So like x and y are the floor, and z is, going up to the ceiling. So like the xy plane is the floor, z goes up to the ceiling, and we want to know, given x, y, and z, given the dimensions of the room, what is this distance from A to B? And we can actually do this using the Pythagoras Theorem, but it's we have to kind of apply it twice. So we're going, picture the room, just look at one corner on the floor, and then just like going, not just another corner on the same wall, but go to like diagonally across the room to the other corner on the ceiling. Now let's do this by looking at a top picture. So let's say you're looking down on this room. So it's a rectangular room with dimensions x and y. Here's point A. Let's call this point B prime. So B prime would be like this point on the floor underneath point B itself. So just to give it a name. And let's call this distance D1. That's just the distance, just across the floor to the point directly underneath B. So we'll call that point B prime. And we can see that D1 squared equals x squared plus y squared. Okay, now let's look at another perspective. Now we have a triangle, because we have this line here that goes across the floor. And so let's just redraw that. Let's say this is D1. This is going across the floor. And then remember point B prime is directly beneath B. So that distance is Z. And so we have this triangle where this is the actual distance from A to B. And we can see from this triangle using the Pythagoras Theorem that D squared is D1 squared plus Z squared. But D1 squared is x squared plus y squared. So if we plug that in, we get D squared equals x squared plus y squared plus z squared. So it's kind of like a three-dimensional Pythagoras theorem. And again, so we define the magnitude of a vector regardless of the number of dimensions. Like you could have a vector with, say, 100 dimensions or whatever. Say it has A1, A2, A3, A4, so on, however many dimensions it has. The magnitude of A would be the square root of A1 squared plus A2 squared. And you just add up all the components, no matter how many they are. And you square them, add them up, take the square root. And that's the magnitude of a vector in whatever number of dimensions that vector exists. And again, that could have an actual physical, something that we could come across in a class like this, like finding the distance from that corner to, like on the floor to the opposite corner on the ceiling. Now we know how to do that. So, yeah, we could define a vector going across, and it would be a three-dimensional vector with components x, y, and z. And we could take the magnitude and just get that, and well, then there we go. Okay, so yeah, vectors, kind of a long topic, but just think of it, everything we do in this class, or maybe around half of the things we do, involve vectors. So there's no way around it. We have to learn this stuff. But I'll stop it here. I'm pretty sure. Let's check the notes. I think we covered everything. Okay. There's one more topic, which I'll just skip for now because this has gone on long enough. There's also vector subtraction, like A minus B. But we're going to need that when we talk about the next topic, which is kinematics in 2 dimensions. So just to keep this from dragging on, we'll talk about vector subtraction in the next video on kinematics.